Hi, everyone. My name is Qianshu Lu. I'm a graduate student at Harvard. Today, I'm going to talk about missing scalars at the Cosmological Collider. So by missing scalars, we're referring to scalars whose masses are less than Hubble during inflation. And we're going to discuss a new observational signature for these scalars based on a unique de Sitter thermal mass effect that these scalars have on particles that they interact with. This talk is based on work in progress I have been doing with my advisor, Maurice, and our collaborator, Qianshu Lu at Tsinghua. Now, as a quick introduction, the Cosmological Collider program is a direct parallel with the terrestrial collider we have on Earth. So on Earth, we collide particles in beams, which goes through a high energy collision process. And we infer the physics behind the high energy collision by studying the properties of the long-lived particles produced through the collision process, which we see in our detectors. In cosmological colliders, we are trying to understand the dynamics and physics during inflation through the properties of the correlation functions of the primordial density perturbations being produced that we see in our detectors, which are cosmological observables such as CMB, large-scale structure, 21 centimeter, etc. The Cosmological Collider is very powerful because the energy scale of the high energy collision is set by Hubble during inflation, which can be orders and orders of magnitude higher than what we can possibly achieve at the terrestrial collider in the foreseeable future. Now, in this talk, I'm going to discuss a new observational signature for light scalars that existed during inflation. Now, in the title of the talk, I call these scalars missing. This is because, as I'm going to explain in more detail, these particles whose masses are lighter than Hubble turns out to be difficult to detect through their direct interaction with the inflaton, despite them being copiously produced during inflation. Now, our signal is based on a unique de Sitter thermal effect that the light scalar has, which is essentially a space-dependent mass correction that the light scalar gives to other particles that it interacts with. I'm going to explain the physics behind the signal and our model in much more detail. And after that, I'm going to describe the actual calculation, which was done in Euclidean de Sitter space, and also the qualitative and quantitative feature of the results from that calculation. And in the end, before I conclude, I will briefly touch on some preliminary Fisher forecasts we did for the observational feasibility of our signal. In general, it is difficult to infer the existence of new particles in cosmological collider. So here I'm showing you how a new particle chi might affect the inflaton correlation functions, along with the reasons why these effects are difficult to see observationally. But the distinction between a light scalar and heavier scalar really becomes apparent when we talk about the inflaton 3-point correlation functions. So here is an example of how a chi particle can mediate and generate an inflaton 3-point correlation function. And this kind of diagram have been calculated by many people in the past, as shown here. And what people found is that in the limit, when one of the inflaton momentum, say K3, is much smaller than the two other momentum of the inflaton, the shape of the inflaton's 3-point correlation function has this particular structure where the ratio of K3 to K1 is being raised to this power, where nu chi is a function that depends on the mass of the intermediate chi particle. But from this expression, it's clear that the shape of the 3-point correlation function is going to have qualitatively different feature depending on the mass of chi. So when mass of chi is heavier than 9/4 of Hubble squared, this exponent is going to be imaginary. So this shape function is really going to be oscillatory in the K3 to K1 ratio. On the other hand, when chi is light, this exponent is going to be real. So this is simply going to be a simple power law behavior in the K3 to K1 ratio. A priori, there's nothing wrong with the simple power law behavior, but the problem is that there are many other processes that can contribute to a inflaton 3-point correlation function, including, for example, inflaton self-interactions. And these background contributions actually turns out to also have a power law structure. So what that means is that for heavier scalar, because of the oscillatory feature, it is easier observationally to extract the oscillatory signal out of the power law behaving background, even when the background is big. But when the intermediate particle is light, it becomes much more difficult to dig the power law behaving signal out of the large power law behaving background. So this is why light scalars are more difficult to detect through cosmological collider signatures than heavier scalars, and hence why we're calling them missing. So for the new signal that we are proposing, we're considering the scenario where we not only have one new particle that's interacting with the inflaton, but instead we now have two fields, rho and chi, where rho is heavier than Hubble and chi is lighter than Hubble. And we give some interaction between the two particles. For the sake of having a specific model, I'm going to assume that they have a rho square chi square coupling. And we're going to further assume that the rho particle has an interaction with the inflaton such that it is capable of mediating the inflaton's 3-point correlation function. Because the rho particle is heavy, the 3-point correlation function of the inflaton is going to have the oscillatory feature that is advantageous for observational purpose. But now, because rho has interaction with chi, the interaction between these two fields is going to generate a modification on the rho 2-point function, which is in turn going to modify the 3-point interaction mediated by rho. This modification is going to allow us to infer the existence of the chi field, even though it's not directly mediating the 3-point inflaton correlation function. Okay, so what kind of effect is a chi interaction going to give the rho 2-point function? To understand that, we need to discuss an important characteristic of light scalar in dissimilar spacetime, which is that a light field in dissimilar space is going to have an order Hubble fluctuation in its field value in space due to the thermal kick it experiences from the dissimilar background, which is essentially acting as a background with temperature Hubble. So what we're trying to do is to make rho aware of the chi field fluctuation in space, and then imprint the chi fluctuations onto the inflaton's 3-point correlation functions. But how can we achieve that? Now, in our rho square chi square theory, the leading diagram that generates a correction to the rho propagator is this one. But very soon we'll realize that this diagram is not going to generate the signal we want, because in this diagram, there's only a single interaction point, that is y. And to calculate this diagram, we'll essentially be integrating this interaction point over all of space. What that means is that the rho propagator is going to see the chi field value being averaged over all of space, which is not going to have any space-dependent signal. This diagram has actually been calculated by many people in the past. And what people have found is that indeed, this diagram is only going to contribute a constant mass correction to the rho 2-point function. And there's no space-dependent signal that we are looking for. But if we go to the next order of diagram, which is this sunset diagram in our rho square chi square theory, now we have two interaction points in the diagram, which are individually going to be integrated over all of space. But because we have two separate interaction points, when the 2 points have super Hubble distance, they will be able to see a variation in the chi field values. And this variation in the chi field value they see will lead to a different correction to the rho mass at different points in space. What this means is that the corrected rho 2-point function is going to be less correlated at different points in space compared to the free 2-point function. And this loss of correlation in the rho 2-point function is going to lead to a loss of correlation in the inflaton's 3-point correlation function that's mediated by rho. Okay. So that is the physics and qualitative feature we expect from our model. Now we actually have to calculate this diagram and see precisely what the quantitative features are and whether the signal actually follows the physics we expect. Now to calculate this diagram, we're going to do it in the Euclidean dissimilar space. So a four-dimensional Euclidean dissimilar space is essentially a four-dimensional sphere. And it is advantageous to do the calculation on a four-dimensional sphere because just like how the spherical harmonics have a quantized angular momentum on two-dimensional sphere, the momentum in Euclidean dissimilar space is quantized. What that means is that a free field propagator or free field two-point function can be written as a sum over the discrete dimensionless momentum L vector, where L takes value in integers. Now, if we look at the form of the two-point function more closely, we notice that when the mass of the field is lighter than Hubble, the contribution to the propagator from the term where the momentum is zero, so the zero mode contribution, is going to be parametrically bigger than the terms where the momentum is non-zero. Remember that our chi field has a mass that's less than Hubble. But what that means is that it is meaningful to decompose the chi propagator into the zero mode contribution and the non-zero mode contribution. And the diagram with a zero mode propagator is parametrically more enhanced compared to the diagram with non-zero mode propagator. Now, in terms of Feynman diagrams, that means in addition to the usual perturbative expansion we have in terms of number of couplings, so 0, 1, and 2, we have another expansion in terms of number of zero mode propagator, zero mode chi propagator in the diagram. So this diagram is going to be more important than this one. This diagram is going to be more important than this and more important than this. Now, as I have explained earlier, the signal we are looking for is only going to come from the sunset type diagrams. Now, this diagram, even though it looks like a sunset diagram, but the zero mode propagator of chi is actually space independent. It's a constant. So this diagram is not going to give us the space dependent signal that we're looking for. So really, the leading order diagram for our signal is going to be this half sunset diagram. Now, like I said, the zero mode propagator of chi is a constant. So this half sunset diagram can be decomposed into a one loop diagram multiplied by the constant zero mode propagator of chi. Now, this one loop diagram has been calculated by Maroff and Morrison in 2010 for generic masses. And using their results, we have found that the 3-point inflaton correlation function that is mediated by this corrected rho 2-point function has the following qualitative feature. So again, we have the K3 to K1 ratio raised to the power of half plus minus I nu rho. So this is exactly like before, like the case for free rho propagator. But now the real part of the exponent is being corrected by our signal, which I'm calling with a symbol alpha. And alpha is a function that depends on the coupling structure, coupling constant, and the two masses. But here it's important to notice that we have a plus sign here, and alpha is always positive. And this plus sign is matching our expectation physical reasoning from earlier. Because remember, our signal comes from the fact that the two interaction points are seeing different value in chi. So they're giving different correction to the mass of rho at different points in space, leading to a loss of correlation in the rho 2-point function. Now here, we see that this is indeed translated to a loss of correlation in the inflaton 3-point correlation functions, since a positive alpha means that the function is decaying faster with smaller ratio of K3 to K1. Decaying faster at large distance means the function is losing coherence at larger distance. Okay, so this is the qualitative feature of our signal, which matches our physical understanding. Now I want to show you how the alpha signal actually depend on the parameter in our theory, which is shown in the plot here. So here, remember, our theory has three parameters: mass of rho, mass of chi, and the interaction strengths between rho and chi. And here I'm plotting the value of alpha in the plane of m chi squared and g, where I have fixed the rho mass such that the index mu rho is equal to 1. So we see that depending on the value of the coupling and m chi squared, we are able to generate an appreciable size for the signal alpha. That's the first observation. Secondly, we see that the signal has a degeneracy in the m chi squared g plane, which is as expected, since a smaller mass for the chi particle is going to enhance the signal. However, that enhancement can be compensated by a smaller coupling g. So we have a degeneracy in the diagonal direction in this plane. Now here are similar plots, but for higher values of rho mass. So the index mu rho is increasing. And we see that when the rho mass is heavier, the signal is smaller for the same value of m chi squared and g, which makes sense since again, the signal we're considering is a space-dependent correction to rho mass. But if the original rho mass is large, it cares less about the space-dependence correction it's getting. Okay. Now, as you probably have noticed, in all these plots, I have restricted the range of alpha to be between 0.01 and 0.5. And the reason is for choosing that range is from our preliminary Fisher forecast analysis. So coming back to the form of the inflaton 3-point correlation functions, the 3-point correlation function of the inflaton has a similar dependence on alpha as its dependence on mu rho. The dependence simply differ by a phase. So what we have done is to borrow the Fisher forecast that these authors have done for this signal with alpha equals to 0 for 21 first centimeter surveys, and where they have found that for FNL equals to 1, the 21 centimeter experiments are expected to reach uncertainty for mu rho that's equals to 0.01. Now, assuming the Fisher forecast is roughly phase independent, we have translated this. We have translated their results on the accuracy of mu rho into an accuracy for alpha, roughly 0.01. Now, the upper bound on alpha equals to half is from the fact that when alpha is bigger than half, our signal is going to be decaying faster than the so-called equilateral shape. Now, there's in principle no problem with that, but it's just that the paper we have borrowed the Fisher forecast results from didn't take into account the equilateral shape background. Therefore, for simplicity, we simply cut off the alpha value at half. Okay, so in conclusion, I have introduced a new observational signature for a light scalar that existed during inflation for the Cosmological Collider program, which is through a de Sitter thermal mass correction the light field gives to a more massive field that leads to the loss of correlation of inflaton's 3-point correlation functions. I have shown you our calculational method and also quantitative results. And we have discussed how this signal is potentially observable at 21 centimeter experiments for order 1 chi to rho coupling and the m chi squared that's moderately below Hubble squared. We didn't do a Fisher forecast specifically for large scale structure experiments. However, we expect a similar signal is going to be the signal is going to be observable at large-scale structure experiments as well. Thank you for your attention, and I look forward to your questions. Thank you.